maybe the last thing. It would be very helpful for me if some of you would make notes. Okay? So I will edit them, and it would be a kind of a book, hopefully. So I am going to teach classical physics this spring semester, and I'll go to quantum physics in the fall. Okay. Now let me start with classical physics. One second. I want to show you a person who actually started classical physics. Maxim, is it possible to see my screen?
Yes, absolutely.
Okay. This great guy was called Zenon. And he formulated several problems about physics. There was no physics this day, but he formulated several problems about nature. And the first problem was the problem about an arrow. At time t1, arrow is here. At time t2, arrow is here. What is the meaning of moving arrow? If I just fix it like this, it would not move. However, it moves. So it was actually a Zenon problem. Now, it turns out that this Zenon, okay, let me speak a bit American English. I will call it Zenon puzzle. So it was solved completely only in quantum mechanics. That we will discuss next semester. So it was a equation of inertia of flying arrow. So the next attempt made Galileo. However, his attempt was not quite successful. And final attempt was made by Isaac Newton. So here we may see this man. He formulated the first law of mechanics. he says that inertia is a constant speed of the body. You may ask what the body is. Just imagine a box, a brick. It is a body. And it moves like this with constant speed. And it was called inertia. In the same book, Newton said, the body could also rotate. And he also said that there is some kind of inertia in rotation. However, he did not formulate it. And you know why? If you have a body like this, if you rotate it and throw it this way, it would rotate with constant angular velocity. However, if you take a brick and you throw it, you will find an interesting phenomenon. It was not discussed in Newton's book. That angular velocity, so there are angles, there is a velocity. Velocity is the change, the speed, how body is rotating, is not constant. So Newton had a good idea, but it turns out that inertia is not conservation of the velocity. Okay? Later on, we will come to this. Okay? So the law of inertia is considered to be the first Newtonian law. But already at this moment, Newton forgot rotational degrees. Rotational coordinates. So Newtonian's law would be incomplete. Okay? Now, let us come to the so-called second law of Newton. So first law, incomplete. Then there is so-called second law. And second law was the following. Suppose that we have several bodies. My favorite brick, a ball, say a tetrahedron. body 1, body 2, body 3. Then Newton said, bodies act on each other by forces, and each body has a quantity called mass. And Newton wrote the following. Equals to F to sum of for J non-equal to Y, Fij. And he said that this is a force with which body J acts on body I. So, keeping in mind that the first law is incomplete, we may assume that Ri should be something like position of center of mass. Here I have 0, here I have R1, here I have R2, and here I have R3. And you know what? It turns out that in real life, this law is wrong. Puzzle. Consider two bodies. One has mass m, capital. Another has mass m small.
Professor, I can't see the upper part of the blackboard.
Sorry. Thank you. And we know that there is a gravitational force that Newton found. It is some constant times m over r squared. Now it is nice because if I cut this body into two pieces, I see that this is gm r squared m over 2 plus gm r squared m over 2. However, if we look at the sky, we see Mercury. That is rotating around Sun. So this is an ellipse. I exaggerated a bit. And then this ellipse is slightly rotating. And you can see it in the sky. And piece of this rotation comes from the fact that actual force has this g m times m over r squared plus g tilde m squared times m over r cubed. Now we have this non-linearity in mass. So what does it mean? It means that the force with which Sun is acting on Mercury is not a sum of forces produced by its components. Puzzle. So it clearly contradicts with the second law of Newton.
Andrey, sorry I missed. That's R cube. Is that an experimental observation? Where did it come from?
Yes, you may check it. It's not a theory. You may check it from experiment.
But where did it come from? Yeah, how did it appear for the first time ever? I didn't know, I have never seen this formula. Where did it come from? From some theory, from experience, where did it come from?
So this piece came as an effective theory from general relativity. But it was
General relativity, the general relativity gives this contribution. Okay,
yes.
thank you. Thanks.
Yes, but appearance of this contribution could be measured in how Mercury moves on the sky.
Understood, thank you.
Now, here we see some kind of asymmetry. And with this asymmetry, we have to conclude that there is another term where masses are interchanged. Because the law should be universal. Sorry. And then it would mean that it is not true that acceleration maybe not acceleration, that the way how bodies fall does not depend on mass. So different body fall differently. You just put here something like M R two, sorry, not two dots. You divide by M, and you see that acceleration depends on M. So different bodies fall differently. And here we come to contradiction with another great man. Let me show you this great man, okay? Galileo Galilei, who said, who not only said, who made the first consideration in theoretical physics. He said, let us consider two bodies, M1 and M2. falling over the body with a mass m. And he said, let us assume, that's what Galileo said, that, say, heavier, that if m2 is greater than m1, then body 2 falls faster. Okay? Then he said, assume. Then make a joint body, m1 plus m2. From the one hand side, it is even heavier. Okay. Has more mass. Than m2. So it should fall even faster. On the other side, he said, so m2 falls faster than m1. So body m1 keeps it back. However, body 1 pulls it back. So it should fall slower. Contradiction. Okay? So that's what I wrote here. So they should fall with the same acceleration. And this consideration is what known as mistakenly. It was mistakenly considered as Galileo derivation of equivalent principle. Okay, so we see that something is wrong in all this.
Andrey, what is the equivalence principle? Would you please remind?
Equivalence principle says that all bodies fall in gravity independently on their mass.
Okay, thank you. Mhm.
And now let me come to so-called third Newton's law. So Newton formulated it as Fij equals to minus Fgi. And you may think, is it exactly what we need? So could we imagine a world where this happens but that could not exist from our intuition. So let me make here what I called Newton's rotator. I have two bricks. And let me imagine that something that one force goes this way, another force goes this way. And let me connect them by a stick. Then I will get immediately perpetuum mobile. These things would rotate faster and faster. I call it Newton rotator. You see, I'm quoting books. I'm not quoting journalists. I am reading originals. Now, people are trying to correct it. And then they say that, okay, Fij could be proportional to what? It could not go like this. It should go like this. But how it should proportional? So first guess would be Ri minus Rj. But in real life, it's not like this. Suppose one body is the composition of two bodies. This is charged positively. This is neutral. So it is like proton, and this is like neutron. Okay, I'm starting to teach you something about elementary particle physics. And suppose here I have a proton. Then the direction of repulsion is like this. However, direction between center of masses is like this. So this is also wrong. You see, that's why when I was a schoolboy, I realized that I cannot read books on physics. So for normal mathematician, this is full of contradiction. So I just explained to you standard story from the high school program about Newton's law. So I hope that after me talking like this, you should understand that, I don't know, quality of your education, but most of high school education on physics is garbage. So mathematician could not tolerate it. Well, it is good to correct Newton, okay? So one has to step up and say, Newton has had good ideas. However, these ideas have to be corrected. Now we will come to corrections. So ideas are great and they could be corrected, but the thing that you would need is the axiom number 0. there is an elementary body. Called material particle.
Excuse me, Professor, we couldn't
Yes.
see the upper part of the whiteboard. Thank you.
Sorry, thank you. Called material particle. So these material particles are completely described by their position. So they are not bodies. It's a new object. They are described by their radius vector. To ask what does it mean to rotate material particle has no meaning. And all bodies are made out of material particles. So then the law number 1 about inertia makes sense. We should not talk about rotational inertia for material particles since this thing has no meaning. Just because material particle doesn't have a rotation. Interesting thing is that elementary particles rotate in some sense, but the meaning of their rotation would be clear at the very end of my course. How electrode rotates. Or what is the spin? To understand it, you should know a lot. And I will provide you with this information.
Andrey, how does it work with the law? I know from school that the force is proportional to the mass, is proportional to the acceleration, and acceleration is more than the position of a particle. It's a position plus the acceleration, not just the position. It's some second
Oh.
derivative.
Acceleration is a second derivative. Acceleration
So
is the
position has been a function of time.
yes, of course. That's what I assumed. Maybe I forgot to say that position is a function of time. Otherwise, the very meaning of this.
Point in the space position.
So here we have a radius vector of the
Professor,
material.
your focus is not on the board. Focus.
So now I think focus is okay. Okay. You see, my camera is too smart. It wants to improve from time to time. And that's what it does. So this is called acceleration. So the zeroth law, the first law should be written like this. If there are no forces. Okay, now inertia is clear. Let us try to correct the third law. Law 3, correct. Fij is actually parallel to Ri minus Rj. So it has meaning. For material particles. Okay? And now, let me come to the second law and its correction. The second law from this writes as follows. dri d2ri over dt squared is the gradient of ri of what? People put here minus sign. Of the function sum of I and j going from 1 to n is the number of material points. And here we have u that depends on the moduli, on the modulus between Ri and Rj. And also on the type of this particle. So this is a gradient or partial derivative. Now, I can solve the problem with mercurium saying that Newton was a bit wrong, assuming that U could depend that U could depend only on two material points. Actually, this thing allows proper generalization. And here I write U that depends on R1, Rn, that is invariant under translations and rotations. Not necessarily pairwise. Not necessarily pairwise. This thing. Now you may ask, how does it happen that people formulated everything in terms of forces and kind of found no discrepancy for several hundred years. Basically, it's because U is not a fundamental concept. In quantum field theory, U is generated by fields. By field exchange. And field could be linear or nonlinear.
Andrey, what is a field exchange? Assume I
Okay.
know what a field is. What is a field exchange?
At the moment, it's a picture. And I will make it, now I will draw a picture. We are not assumed to understand it. But you may keep it in your mind. Because later on, I will explain this picture from the first principle. Okay, so here it is good to go to philosophy before Newton and Galileo. So before Newton and Galileo, people were thinking about ghosts. That there was body one, that it emits ghost. And this ghost goes to the body two. And instructs body two how to move. So this was so-called scholastic philosophy of the Middle Ages of Europe. And then Newton came and Galileo came, saying that there are no ghosts, that we do not need them. Later on, this idea that body produces something that acts the second body came back in the notion of the field. So let me tell you what you probably know from elementary physics. That you have a charge, and this charge creates electric field. And then this electric field is acting on another charge. So field somehow transmits forces. But electric field could exist alone without any charges. Like now we see radiation from the early ages of the universe called microwave radiation that comes to our detectors from all over of the universe. So field could exist without source. It is something that we know for sure. But in some approximation, you may think that you need source to create constant field. So the picture was like this. Body or the particle one, body or the particle two, and they are exchanging fields. And if they do it this way, then U would be sum over I non-equal to J, U, I, J, from these exchanges. However, it is interesting.
Did I
Well-
understand correctly that the vertical coordinate here is time? You didn't specify, you didn't draw it.
Yes, yes. This is time. These are particles. These are fields. So fields are the modern incarnation of the Middle Ages idea of ghosts that you send, that are sent from one body to another body. Now, interesting thing can happen. Then these fields could be nonlinear, and graphically, it is something like this. So if they are nonlinear, we have the following interaction. Just imagine that first interaction is proportional to M1. And here we have something M2 and M2. So altogether, from this, we have potential that is proportional to M1, M2 squared. Or even better. Suppose I have 3 elementary particles. And then I have such an exchange. Unfortunately, so these lines are not intersecting. So here I have such potential. IJK. And this is what was completely missed by Newton. So I will make a break. I just want to say the following. Here I see some cultural difference between East and West. And I assume that mentality of the West affected Galileo and Newton a bit. It is the idea of the force. So what is the force? Force is a kind of a violence. Subject 1 forces subject 2 to do something. That's what we call force in ordinary life. And people project this social practice to science. So force comes from violence.
Andrei, I couldn't see whatever you are writing. It sounds interesting, but I couldn't see it.
Okay. So force is about violence. However, if I have this UIJK collective potentials, it's about harmony. So this collective potential points of view is kind of, so this is a Western point of view. At least old Western point of view. And this harmony is Eastern. So you see, trying to be in harmony, where particles altogether are trying to minimize their potential, is a very Eastern idea, okay, from my point of view. So now we will do the following, and I hope I will do it all the time. I will make a 10 minutes break. Then I encourage you to ask questions, because I need to know you. So now you probably know me a bit, but I want to know you. So actually, it's very important for the course. I need to know my audience. I can give lectures in many styles. So I'll try to adjust. So please, write me questions.
Andrey, I would prefer to be able to see your face more of the time, because a lot of the time I could only see your glasses and your forehead, but not your smile and not your face. So if you can
Okay, thank
somehow
you.
be
Thank you.
just camera. Yeah.
So we will start in exactly 10 minutes. Okay? And I will ask you to give questions again. I switch off my video just to show that it is a break. Okay. So let me continue.
Can we have some questions before, I guess?
Sure.
Well, okay, so I think, so I recall that you wrote the gravitational force between the big mass M capital and the small mass M small. And then you take apart like the big mass, you turn it into, you cut it into halves, two halves, and then you write it as a sum. You write the force. And then after that, you have the issue with the mercury. So what's the relation? I mean, what's the connections between cutting the big mass M into two halves and then with the issue with mercury?
Okay. So when people write down force, they have this type of force. And if you have this type of force, you have elliptical motion. And this axis of ellipse are rest in peace. But if you add extra term, and it has to be like this by dimensional, and then because of this cube, this axis starts to rotate.
Right.
Now the question is how it happens that we have mass square. Here is the sum. Would the force be the sum of attraction to first half and the second half? I could not have m squared there.
Right.
The dependence would be linear.
Yeah.
So we can see here nonlinear dependence.
Right.
So important thing is nonlinearity in maths. And actually, it is because potential in terms of elementary particles is not just pairwise potential.
Okay, like cubic interaction, you mean?
Yeah, yes, cubic interaction, yes.
Okay.
At the
Well,
moment, at the moment, we may call it cubic piece of potential.
Okay. Yeah. Interaction. Yeah. Okay. But I mean, the second question would be you wrote the symmetric term for this extra G tilde term. So you wrote the one with you know, like with small mass squared now. So I mean, the first one is understood coming in as effective term from general relativity, but does the third term, this one, comes also from GR?
Of course, because
Okay.
because the force that is a gradient of potential, and potential should be, so for potential we don't care which mass we call first and which mass we call second.
Yeah, I mean, okay, but that, I mean, so which well, there's the Einsteinian equivalence principle, right? So which is like I mean, almost this. Does this contradict that things?
I am making a provocative course. My course is not like courses given by other people. I am not repeating. I am concentrating on points that are mostly misinterpreted in the literature. So Einsteinian principle should read as follows. When m goes to 0, then there is a universal term. Only if we ignore the self-effect of the mass that comes to the body. Only in this case.
Okay, so when we ignore the third term, then we are consistent with the Einsteinian point of view.
No, it's not Einsteinian point of view.
Well,
So
yeah, okay.
Einsteinian point of view says that if you consider the particle of negligibly small mass, its acceleration depends only on geometry. So this is the proper reading. So if you ignore this m squared, you have term linear in mass. And this is m over r squared, m squared over r cubed. May be interpreted as a change of geometry.
But I mean, sorry for just repeating the. So how come the third term appears from the Einsteinian theory of relativity, which is formulated by gravity, but the same way it appears there was.
It takes since it has small m squared term, it takes into account gravitational field produced by the small mass.
Okay.
Because the small mass is also a mass. It produces some gravitational field, and we need to take everything into account. So you may say that big mass changes geometry and small mass is small enough such that you can neglect how it changes geometry. But actually both bodies are equal. Even one is big, another is small. They both change geometry. And we see the reaction. Okay?
Yeah.
Otherwise, it will be a contradiction. Suppose we have one small body, one big body, and small body is not changing geometry.
Okay.
Then let us take billion of small bodies. They will not change the geometry. However, if we have billions of small bodies,
yeah,
they form a big body.
Yeah. Right. Yeah, I mean the usual formulation of GR assumes that there is one big body that changes geometry, and the other is like point particle, which is like really right. And
yes, that are like so in the approximation where we can that is linear in this small body mass, we have this. However, there should be equal. Okay.
Okay.
So by the way, here I would like to reply to some of the written questions. So people discuss Wikipedia and all this. So please do not trust Wikipedia. Trust your own knowledge. So what is written in Wikipedia could be a misinterpretation of some deeper fact. Okay, so it would be easy to misinterpret it. And in this course that I'm going to give, I will focus mostly on ideas and not on technical details.
Hi, Professor.
Yes?
Can I ask the next question? Well, my question will probably be a little bit retarded. I'm a high school student, and like I could only get a general idea of those physics concepts you stated. Like I could get a general idea, but for those equations, I cannot comprehensively understand those things. So like I just wonder that like what some study materials can I get and like previewed before this course and like can better understand the the things we're going to cover in the future.
You see, I will try to make this course as self-consistent as it is possible to do. Because at the moment I wrote only one law. And this is second derivative of Ri over t squared is what? Is minus d over dRi of potential that depends on R1, Rn. So this is the only law that I wrote.
Well,
So-
but like the equivalent equation and like the effective theory from like for the force, which declares for the first law of the Newton's first law, like those equations I cannot quite understand them.
Okay,
Yeah.
so it is enough to understand this equation. So I started with correction. Okay.
Yeah.
assume,
Yeah, I could get the general idea, but like for the specific mathematical expressions, like I think I still need to like learn some other things in order to understand them. So like my question is simply like, what should I read and like should I learn in order to understand those expressions?
Okay, in order to understand this expression, you need to know calculus. So
Okay.
calculus is a thing that is required.
Yeah,
We will
can you
not
be more
explain calculus.
specific?
Calculus means partial derivatives. That's all what is needed. Because I use partial derivatives here. Here I have the second derivative in time. Here I'm using this symbol d over dr I. So what does it mean? The particle Ri is a set of coordinates Ri1, etc. Ri d. D is the dimension of space. So what does this symbol mean? This symbol means partial derivative with respect to Ri. Let me call this index mu. So let me write everything in components. So here we have this equation. So you need to understand what partial derivative is. And you
Oh, I
need to
get it. Yeah, I get it. So I will preview this topic of calculus. Well, I actually haven't covered this before. Thank you. Thank you so much.
Now, after I wrote this equation that actually replaces the second law of Newton, together with the third law of Newton, I want to formulate the following theorem. Ri squared over 2 plus u of R1, etc., Rn is conserved It's a theorem. How can I prove it? Let me differentiate. Here I'll have mi, ri, dri over dt. Sorry, d over dt. d2 ri over dt squared. And 2 goes away because of the first square. And here I have a sum over r. And here is the second term. I have partial derivative over dri, and here I have dri over dt. Then I take this thing out. And I see my original equation. That's it. And such two-line calculation is called conservation of energy. And this object is called energy. So this object is the sum of two terms. First thing is called kinetic energy. Second term is called potential energy. And for the system, total energy is conserved. Later on, we will come to derivation of this equation from different points of view. It has
Okay, a short
Yes.
question for I in this equation is I coordinate components or I particle? I want to know.
I stands for number of particles. Number
Oh,
of,
okay, I see. Okay, thank you.
so we call it not a particle, we call it material point.
Material
You see?
point.
You see,
No.
it's a point because electron is an elementary particle. However, electron has a spin.
Spin. Okay. Spin.
Yes.
Okay.
Yes.
Okay.
So instead of saying spinless elementary particle in classical physics, people say material point.
So we do not consider the spatial coordinates like x, y, z or this kind of thing in this equation.
In this equation, R is x, y, z.
Oh, okay.
It's a vector.
So your gradient partial Ri is a symbol, just a symbol, not like we often use in mathematics like partial x, partial y, partial z, or this something like that.
Yes. So D, you're right. So it is kind of a standard thing. It is also a vector. D over dx, I, D over dy, I, D over dz, I.
Okay. So another simple question for this part. You mean that we start from the Newton's law to this expression about the potential. So I just wonder every force can be expressed as a potential. Is it right? Oh.
So you see, it depends how we should define forces. I told you that Newton made a mistake.
Okay, okay, I see. Okay, okay.
Okay, so now this is a corrected form of Newton's law. So I was talking about Newton because most of you studied physics at school.
Yeah, yeah. We studied the force for the right hand side. The
Yes,
force.
yes, so you were studying force. And what I told you? I told you that the concept of body is a misconcept because it could rotate, and Newton says nothing about it. I also told you that the concept of force is a misconcept because it is wrong that body act on each other by force. What
Okay.
actually happens is the collective potential that in some cases would be replaced by pairwise potential in some particular physical systems.
But sometimes we often, if a force, I also want to talk about force. If a force can be written as a grad as a function, so we often call this this force is a it's a scalar function can be written as a vectors.
But how can you say that it is a force? You may say that it is a reaction of the particle number I from the action of all other particles. So you may say that everything is acting on a particle.
Okay, okay, on the particles.
And these reactions could not be summed up. So I will have here only pairwise use. I would say that there are forces, and then it is meaningful to sum them together.
Okay.
But here you just cannot sum them together.
Yeah.
Summation makes sense only summation makes sense only if U is a sum ij u ri minus rj. In this case, you may say that you are summing forces. If you have such an expression, you are not just summing forces. So
thank you.
that's why I emphasize this Mercury example, saying that interaction between bodies, between particles, is nonlinear. Okay, so there are cubic terms.
Okay, thanks.
And you see, I have to explain all this. This should be explained in high school course. But people forget to explain this. They quote Newton without correcting him. Okay, Newton made a huge step. But when you make a step, after this step, you need to make a correction. And corrections should go to texts, to textbooks that you study at schools. It's one thing.
Hi, Professor.
Another thing is, yes?
So in this general form of potential, there's also Ri term in the potential U. So are we allowing like the field generated by the particle itself to act on itself?
So it's a good point that you are asking. You may ask, why we are not saying that there is something like U of R itself? So it is possible. It is possible to consider such thing, However, in this way, you typically break translational invariance. Okay? So it's not bad to break translational invariance. You see, when I was writing it like this, I also implicitly assumed that U was invariant under the following symmetry. URI plus constant vector C equals to U of Ri. Okay? I assume that. So, if I assume this, when U depends on Ri, it is just a constant. However, if I violate this assumption, I can very well have U depending on Ri. So let me give you an example showing how it could happen. Suppose you have many light particles and the sun, and potential is invariant. Now you may think, okay, sun sits still, and here you have particles. So here is the sun, and here we have particles. All right, like R1, R2. So there will be potential between R1 and R2. Like particles are charged, and they repel or attract electromagnetic. However, there was also a sun I interaction. That was Ri minus R sun. I may consider this as potential that you are asking, because position of the sun violates shift invariance. So one may also consider this. Now let me kill the notion of force. Okay, there is another reason not to believe in force, because there is so-called Lorentz force. You have a particle that is moving in magnetic field. Particle, magnetic field. And we know that it accelerates proportional to the vector product of and magnetic field. Okay? With a charge. So this is called Lorentz force. And here we see that acceleration depends on velocity. And you may ask how it could be. Newton never mentioned acceleration that depends on velocity. Right? So there could be something very wrong in Newtonian's formulation of the theory. That's why, even being improved, it's not the final understanding. Okay? So this is not a potential force. You may ask, what's going on? How could it be? How could force depend on velocity? Of course we will study it. Now I'm opening puzzles for you. You see, in order to study something, you should be puzzled. So you should be interested to see what is going on. Okay, now let me make another important remark. Okay, once again, I'm speaking based on the school textbook. And I'm speaking about well-known facts. Now, another question. If there is the zeroth axiom of Newton, that he never gave, then there is a natural question. What is the mass of material point in improved Newton mechanics? So let me call this improved Newton mechanics. And here we are coming to the very interesting issue. It's a very deep issue. And this issue goes all the way towards quantum field theory, and it is called renormalization. So renormalization says the following, in general.
Andrey, sorry, I couldn't read the acronym. The question is, what is the mass of a particle in an acronym which I missed?
Repeat, could you please repeat the question? Your sound.
It is written on. Yeah, I have some internet issues. Andrey, it says, what is the mass of the particle in some theory which was mentioned by an acronym? I couldn't see behind your forehead. Would you please? Yeah. What is the mass of a material point?
Improved Newtonian mechanics.
Improved Newtonian mechanics.
Yes.
Okay, and improved means taking into account general relativity.
Of course
or something else.
not. Improved. No. So improved means. So what have I did? I said that Newtonian mechanics, without the notion of material particle, has no mathematical meaning. It is incomplete. And contradictive simultaneously. So in order to save the game, we should go from Newtonian mechanics as written by Newton. You may read his textbook, his book, by your own, to improve Newtonian mechanics. In improved Newtonian mechanics, main thing is to introduce axiom 0. So improved Newtonian mechanics is about material particles. It's not about bodies. And then you can answer most of the questions of self-consistency. Improved Newtonian mechanics described by this equation, okay, only one equation of improved Newtonian mechanics. Not three laws. Only one equation. And okay, together with the statement that U of Ri plus C equals to, okay, R1 plus C, Rm plus C equals to U of R1 Rm. So this is the condition 2. 1 and 2 are equations of improved Newtonian mechanics. And in improved Newtonian mechanics, you may answer all questions except the question of the Lorentz force. And in improved Newtonian mechanics, you can get conservation of energy and also conservation of momentum. Consider this object. Let me call it momentum. Then dp over dt is, I plug this in here. Sum over I, U of all r's, dri. That is 0 because of this. So star and 2 stars is called improved Newtonian mechanics. However, just to write improved Newtonian mechanics, I need to have axiom 0 about material point. Without material point, it makes no sense.
So let's call it DM, yeah? I am half joking. For Democritus, let's call it Democritus mechanics. It has just...
Yeah. Okay. DM. DNM. You should not eliminate Newton.
Elementary particles with their radii vectors, and masses.
Yes? So it's better to call them
And one
elementary.
law. I have some connectivity problem.
Yes. One law and one extra thing. And you have everything. Okay. I still want to make this point. That I am coming to the very important issue of renormalization. So this issue is deep. So I will just start it right now, and I will continue tomorrow. So mostly we would have seminars, okay? But I need to put in some material for you. So tomorrow it will be half lecture, half seminar, okay? So renormalization says, could we determine these masses from experiments? And the answer is that in Democritus Newtonian mechanic, in DNM, we cannot determine, we can probably not determine MI from experiment. What do I mean by this? I mean, just imagine that now we have bodies like bricks. Each brick is made of billion elementary particles. And just imagine that potentials between them is such that you cannot take one particle out of this brick. So the only thing that you can do is to break brick in pieces. But then you may say, let me do the following. Let me say, take M and divide M by some number K, natural number. Take number of particles on the brick. Let me call it NB, number of particles. And do like this. So M goes to M tilde. N goes to M tilde equals K times N. In this case, the density would be the same. If I break brick into two bricks, I will not see this difference. This is actually a symmetry. And that's why I cannot see in this model fundamental structure of matter. I cannot see atoms. To see atoms, I need some sophisticated experiment when I can take particular particle out of a brick. How can I do it? How can I see this particular particle? My devices that I use in observation could be not precise to see this small particle that is taken out of the brick. So they may be like this. And in this way, I would say that in this theoretical model, I have this renormalization group. So when I'm thinking about bricks, when I'm thinking about machines, I cannot find this fundamental mass from experiments. And the fact that I do not see it from experiment, however, it is a piece of the axiomatic description. This phenomenon is called renormalization, namely two theories with fundamental masses m and m tilde could lead to same experiments if I'm thinking only about bricks and its pieces. So it is a very deep statement. That fundamental theory, D and M, its fundamental theory contains this mass. However, when we do experiments, we don't see it. We don't see it. So this is used in modern quantum field theory. When people say something happens in the theory, and some people call it ultraviolet cutoff. Like maybe our space-time becomes a lattice, or something else happens. However, at our low energies, we just don't see it. And this phenomena called renormalization first appears when we go from contradictory Newton mechanic to mathematically complete DNM. Okay? I'll continue tomorrow at the same time. So, here is my email. Sorry, yes. This is a number. Please do not hesitate. Please do not hesitate to ask me questions. Because lecturing is an interaction. So my goal is to transfer some knowledge to you. And I cannot do it if you would not ask questions. So I'm very grateful to everybody who asked questions. Okay? It's very hard to play table tennis with the wall. It's very good to play table tennis with a partner. And you are my partner. So we are making the course together. Your questions would make me think how to answer them, and it will improve the course. So just don't think that you are interfering. It is the pleasure of having interactive course. So just come in. All of you are very welcome. So do you have any final questions?
Yes, may I have a question?
Sure.
Firstly, it's a bit of historical question that I have known about the argument made by Galileo about that the two bodies with different mass and they actually fall with the same speed. But I mean, be honest, I feel the argument doesn't seem to be very complicated. So my question is, why someone before him, in those long periods of time, nobody came up with arguments similar like that?
May I ask first what was the Galileo's argument? I do not know. Thank you.
Oh, I explained it today. So Galileo's argument was, when we have two bodies, M1 and M2, and suppose that heavier body falls faster. Just imagine. that the acceleration depends on mass. Then it falls faster. It is not falling so fast. Then idea is, let us combine them in a single body. The mass would be a sum of masses. It will be even heavier than M2. So in this case, it would fall faster.
Understood. Thank you. Brilliant argument. Somehow I missed it. Thank you. Yeah,
Okay.
got it.
Okay, but at the same time, this slower piece would pull it up. And that's why it should fall slower. So there is a contradiction. And this argument is the first argument in so-called theoretical physics. So all theoretical physics started with this argument. With some correction. First correction is this argument is too theoretical. If you actually be in Florence, and if you actually throw balloons from the tower, you may see that balloon that is filled with air and balloon that was filled with metal would fall differently. In particularly for a balloon filled with air, it will take enormous amount of time to go down. Because there is an air. And surprisingly, Galileo even missed the notion of air. Air was discovered by Torricelli like 30 years later. So Galileo argument is not true if there is a third agent. If there is a third agent. And also Galileo argument is based mostly on the existence of force. And I'm telling you, that force is a wrong notion.
Yeah. Okay, yeah, I get this. And I have another question that I know that Newton wrote his book with hundreds of pages, and people later on summarized them with three principles.
It's wrong.
It's wrong?
You see, I also thought that he wrote something detailed and people summarized. So it was my mistake several years ago. So I decided I don't want to look at the summary. I don't want to go to Wikipedia. So okay. I opened the Newton's book and studied it from first page, okay, to the middle, where I studied the relevant part.
Is it fun experience?
So Newton wrote exactly what I told you. I'm very close to Newton, just only I'm saying it in English, not in Latin. As these days, all reasonable people were writing in Latin in Europe.
I see. And I mean, do you enjoy reading his original text?
Of course not. because it was easy for me to see parts where he was unclear, where he was omitting something. Like I found this idea of inertial rotation. So somehow he understands that it is inertia, but he cannot say it clearly. And most problem, of course, is the notion of a body and the point particle. He never says that bodies are formed of point particles. And to describe the notion of point particles, it is enough to do what? It is enough to specify something like force. He always speaks about bodies, and body could rotate. And he never wrote a law for rotation of body. So the only thing that one can imagine is that if you cut body into pieces, they could rotate around each other, but all this is not clear. Like suppose he would consider like Earth and the Moon. So they are going around the sun. However, they have some internal motion. How to determine this internal motion? But the most interesting thing is, of course, a rotation of a solid body. Just throw solid body in the air, and you will see how fancy is its motion.
Yeah.
It doesn't have a constant angular speed if the body is not symmetric. And there is a deep reason for this. And we will come to this deep reason later on.
Okay, thank you. That's very helpful.
So I want to ask some question, and I couldn't understand the democracy Newton mechanics you just told before just now. You say that the bricks has broken in several pieces, and why the forces has become the n times larger than before?
Okay, no, it's not the forces that become n times larger. So let me consider one-dimensional brick. It's a stick. Okay. Let me consider a stick consisting of 3 particles. Okay. Then I can say, and each of these particles has mass m. Then I may say that so I started this idea. I will continue next time, that I could replace it by a stick consisting of 6 particles, each having mass m/2. Just imagine that the length is the same. So the mass of this and mass of this are the same. And presumably the mass is something that I can measure. That I cannot measure microscopic structure. I can measure the overall characteristics, like the mass of this stuff, or position of its center of mass, or its rotation. Then, if I have here not 3, but n particles, and here 2 n particles, I could not distinguish between this picture and that picture.
Yeah.
Because I will go to such objects like density. I would continue, I would think that it is almost like continuous, and I can cut it in pieces. But I will never see the mass of elementary particles. But it's exactly what happens when we do something with solid bodies. When you cut solid bodies into pieces, you are never cutting it up to elementary particles. Because in 1 gram of water, you have 6 to the 10 to the 23 molecules. Okay, in 1 gram you have this amount of molecules. Okay, 5, 20. So piece, so when we consider piece of matter, it contains billions of billions of billions of billions of elementary particles. But we are working with pieces of matter. We are not working in our life with elementary particles. Like my marker. I'm working with my marker, not with elementary particle of my marker. I can throw my marker as a solid body. In order to see the structure of my marker, I need to go to the very complicated device, like electronic microscope. But at the time of Newton, there were no electronic microscopes available. Or I have to dissolve my marker in the acid and study Brown motion under the microscope. It's also possible, but it is quite complicated experiment that was not available at Newtonian time. So that's why in Newtonian, in Democritus Newtonian mechanics, the notion of, there was a notion of renormalization. And that is kind of important notion. Okay?
Okay, thank you.
Okay, 1 second. Ah, yes. I want to show you this person. Ah. Isn't he beautiful? Actually, he had a hard life. So I'll try to show you all people who were involved.
Excuse me, who is who is
It is Democritus,
Democritus?
who had the idea of elementary particles. 2,500 approximately years ago.
Yeah, Greece time, right?
Yes, Greece time. But he could not make it into formulas. And of course, Newton knew about his ideas, but he never mentioned. He was considered to be out of the mainstream. People consider it as a very original idea, but not in the mainstream. Okay? So let us do the following. So let me let people leave okay? But if somebody wants to ask questions, they could stay in the room and ask me, okay?
Oh, Andrey.
Yes.
Hello. I'd like to ask something about renormalization.
Yes.
Renormalization is regarded as a tool originated from quantum field theory. People use it to remove some singularities. I don't know why we have renormalization at this very elementary stage on Newton's mechanics.
Okay, let me try to explain. So of course, I know the story of normalization. Okay, since I'm a specialist in quantum field theory. But actually, you see, when I'm teaching physics and when I'm thinking about physics, I'm trying to find the roots of ideas. Okay. So when I was thinking about Democritus Newtonian mechanics, I of course found similar phenomena. We have a microscopic theory with these fundamental particles. And we have a microscopic theory about our observations at low energy, big scales. And renormalization is a statement that you can make prediction about low energy theory. So now I'm speaking in terminology of quantum field theory, independent on what happens at high energy. So renormalized parameters are density, total mass, etc., total length. These are so-called low energy parameters. And such thing as mass of fundamental particle or fundamental spacing between particles in the stick are microscopic parameters. And renormalization, idea of renormalization, that you can speak about infrared or low energy theory without having detailed information about ultraviolet. So you may change. So in quantum field theory, you may do the following. You may change the ultraviolet coupling constant and cutoff to another ultraviolet coupling constant, a new cutoff. So this is the ultraviolet chain. And it would not affect low energy. So that's how it is treated in quantum field theory.
Right.
But here I see the same phenomenon. So the role, if you wish, the role of ultraviolet coupling is played by the fundamental mass. The role of cutoff is fundamental spacing. The infrared objects are like density, masses, okay, lengths. They do not depend on these fundamental scales and fundamental masses. And this phenomena is similar to renormalization in spirit. That's why I call it renormalization. If you wish, I can prove you another renormalization that could happen even before DNF. It is completely unphysical, but you may think about it. There was a model when the Earth is in the center of the world, and there was a sphere that was called cellular sphere, as far as I remember. And stars were considered as points here. Okay? And then one may ask a question. What is this radius? A radius to the sky. And you may say that you can change this radius from R1 to R2 and change the brightness of the star corresponding. So star has characteristic, it's a brightness.
Yes.
So since we see the star, we see some energy coming out of the star, some amount of light. So if star is closer, its brightness could be smaller. So here we have brightness of the star. Would star be placed at R1 and R1, and this is equivalent to brightness at R2 and R2 with the brightness of R2 being something like 1 over R squared. So the closer you are, the lower is the brightness that you need to get the same phenomenon. Okay.
So we have a similar pattern.
Yes, so we have similar phenomena. We can treat this cellular sphere as if it exists. And we put here not ultraviolet, but big infrared parameter, called this radius, and adjust brightness of stars corresponding. The observation would be the same. So it's another renormalization that people had a long time ago, that people could have a long time ago. That observing stars, they could not determine this radius. So in Greece, they determined the radius of the Earth, but they could not determine the radius to stars. So they consider these stars to be on this sphere. So what is the radius of this sphere? You can run out renormalization argument. So here are two renormalization things in the ancient time. So what we have nowadays is just the continuation of the same phenomenon. And the only person who never studied history of science and who is never thinking about old models could say that renormalization appeared only in the period of quantum field theory.
I agree with that.
Okay,
Yeah.
Another renormalization was Maxwell theory. Maxwell theory of gas. Once again, there was a lot of particles moving and hitting the walls. And you can get relations without getting the mass of the particle. It would be the third renormalization. It was the third renormalization. So before this relatively modern quantum field theory renormalization, there were at least 3 theories that had renormalization. So it is not correct to say that renormalization appeared in quantum field theory. So I would say that renormalization in quantum field theory is just another incarnation of renormalization idea. I'm sorry to use this Buddhist image, okay, Buddhist concept of reincarnation.
Yeah, they share the common idea behind.
Yes, yes. So it's common idea, and it reveals from time to time in different theory. That you put some parameter inside the theory, but this parameter is either infinitely big
Andrey,
or
I have to interrupt. The idea of reincarnation is Indian, and it
yes, I'm sorry. Okay, Indian idea of reincarnation. Sorry.
So you cut the body into small pieces, and small pieces, just like
Yes,
zooming.
but you see, but you see here the renormalization is not cutting bodies into pieces. Here renormalization is to say that one fundamental particle of mass m is actually 2 fundamental particles of mass m over 2 and s and m over 2. And you cannot distinguish.
Oh, I see.
So renormalization is something that deals with the extra parameters of the theory. Renormalization group is something that is acting here, like in this model of stellar sphere, changing the radius, changing the brightness. The only thing that you have here is an effective brightness, the amount of energy that comes to your eye. So this is infrared renormalization. This is the ultraviolet renormalization. So it's not surprising that in quantum field theory we have just another renormalization. In particular, there is a Polyakov approach to quantum field theory that says that we are studying the critical phenomena on the lattice when the correlation radius is much bigger than the size of the lattice. And in this limit, we have renormalization. So it is Wilsonian / Polyakov approach to renormalization. Wilson said that we have a lattice and we have spins, and then we can say that for vortexes is just one new vertex. But again, we have a lattice. And since we are looking at long distances, we just cannot see the difference. So this is Wilson Polyakov idea of renormalization.
Okay, thank you.
You are very welcome.
Can I ask you 2 questions?
Sure.
So my first question is about the Wilsonian approach to renormalization. Normally, we in the Wilsonian renormalization approach, we integrate out the high frequency modes. But I was wondering if it make any sense to integrate out the low energy frequencies first.
No, I don't think that it makes sense.
Can you elaborate? Because for example, in 5-4 theory, the interaction terms of the low energy frequencies and high energy frequencies is totally symmetric. To me, it's like if you label some terms by high energy frequencies, then you can also label them like low energy frequencies. I don't know from mathematical point of view, how do you distinguish those terms?
So you see, okay, let me try to explain. When you say that you want to integrate something out, it depends on what you are studying. Okay, if you are studying correlators, or you are studying not correlators, you are studying reactions to source. Okay.
Yes.
If your source could bring low energy in the business, you just cannot provide a high energy excitation. So you can just integrate them out.
Okay.
But if you have a source that brings high energy, this high energy could go to low energy. And you need to think about the mechanism that prohibits this.
Yeah.
So why high energy is not going to low energy degrees of freedom? There should be some mechanism. If you have this mechanism, it's okay. So this mechanism could be symmetry. In particular, if you consider your favorite lambda 5-4 model, this could be idea of rotational symmetry. If you have rotationally invariant sources, then you cannot excite angular, or probably you cannot excite angular degrees of freedom. However, I think you can. Now I think you can. So here we have high energy. Representation, say trivial. Here we can get representation R, representation R prime. Something happened and you are back with a trivial representation. In this way, high energy source being singlet generates you low energy representation and with different symmetry that could combine back to a scalar. So that's my understanding. So I never thought about decoupling of high energy from low energy. I always thought about the difference of decoupling low energy from high energy.
Can you explain that diagram? Well, what is R and R bar?
So suppose I have high energy excitation. That is a singlet under some symmetry group. this high energy excitation could create low energy excitations that are in different representations, R and R bar of the symmetry group. So you see, I'm trying to see how, I'm trying to find a mechanism that would prevent transfer of energy from high energy to low energy. In the lambda phi 4 model, there is a phase of field phi, and the phase is a non-trivial representation of the symmetry group. However, there is also a radial piece of phi. Suppose you have a complex field phi, a vector. It could be represented as a matrix that is applying to the field phi radial. And this corresponds to infrared degrees of freedom.
You mean the
If
angle?
potential is like this, you may decompose field phi into radial degrees of freedom and angular degrees of freedom.
Yes.
So angular degrees of freedom are low energy. Radial degrees of freedom are high energy because you have a potential like this.
Ah, yes.
And then you may try to ask in which sense I can have an effective theory for lower degrees of freedom. I can integrate radial degrees of freedom out. It's a good problem. But now you want me to do the opposite. You are trying me to integrate this out, low energy degree of freedom. Now I'm thinking how it could happen that I could integrate it out. Because all high energy degrees of freedom would produce excitation. The only argument that I could see is the following. Is what is called in mechanics decoupling of radial and angular degrees of freedom. In mechanics, there are actually not so coupled. So first argument that I was trying to give was from representation field. But I see that on the quantum level, if I put here energy, I could get excitation in these degrees of freedom, representation and conjugate representation, with the interaction being invariant under the action of the group. And then something happens, and later they could join together to a singular. And I'll be back with something in radial degrees of freedom. You see, I'm trying to integrate angles out. So the only place where I saw this is quantum mechanics, where you can actually integrate angular momentum out. So here you integrate them out, and you get effective potential for radial motion. So this is an example. But this is called separation of variables. This is the result of integrating out angular degrees of freedom. And here you have your radial potential plus some potential. So I take my words back. In some cases, I don't know how to describe them. It may happen that you may integrate out low energy degrees of freedom like this. So it makes sense to call it low energy if U of R is something like, I don't know, like this. Here we have R naught. So here we have high frequencies where you have radial excitation, and you have quite simple frequencies that you have from angular momentum that are L, L plus 1, I mean energy, R naught squared. So you may call it energy, okay, low energy degrees of freedom. It's their energy. And there is, for radial motion, high energy frequencies of this potential. So there are some models, but I do not know how to say it in general. Okay.
Okay. And my second question is, are there any fundamental reasonings why the equation of motion of bosonic particles are always second order, and the equation of motions of fermionic particles are always first order?
So I would say that it is that one can still write equations of motions for the bosonic particle in the first order system.
For example, like what?
Yes. So equations of motion for bosonic particle, okay, could be derived from this type of the action.
Oh, but it's still, yeah, but you can still write express P in terms of phi, and it still makes
Okay, but then it means you are integrating out P.
oh yes.
So if you allow such things, it's not a fundamental reason.
Oh. Yeah. All right, thank you. Thank you.
You're welcome. Okay. So I will wait for 5 more minutes until, okay, for several minutes. Maybe somebody would ask question. It's too late in China, I know. But actually questions are as important as the lecture.
Sorry, Professor, I have a question.
Sure.
I'm still confused that you say the democracy Newtonian mechanism has renormalization symmetry. When you cut one particle into two, isn't that true that your potential also split? And then you require that your potential has certain properties, then your theory has this
Yes, exactly. So
symmetry.
yes.
So what's the requirement of the potential?
Okay. So the requirement of the potential in this case would be approximate linearity.
It's approximately what?
Linearity.
Oh, okay. Approximately linear. Okay.
But you asked a good question. Could we? So it's a good question to study. Suppose we have cubic potentials. What would happen with this Democrit renormalizability?
Yeah, it is not obvious that this democracy renormability is true for every potential.
It's not that obvious. Because if you split in p,
yes.
and if you have cubic terms, then life becomes more interesting. So it's actually a good question about, just imagine that we have quadratic potentials like in Newton's theory of gravity plus some cubic potentials. Okay, so what can we say about renormalizability in this case? And it's a good problem that it's important to study.
Yes, it seems that if you have a cubic potential and you cut your particle into two particles, then certainly your system have more energy.
Yes. So now it becomes interesting. What does it mean?
Okay. Yes.
So it's a very good question. Thank you very much.
Thanks for your answer.
I'm trying to show you that one can actually ask deep questions on the simple material. It's one of the things that I would like to show you. You do not need to have complicated equations and complicated mathematics. You can think about simple models and ask deep questions. By the way, this is a person who put the Earth in the middle of the universe, Aristotle. Okay, as a Russian poet who got a Nobel Prize said, everything has a limit. So we are coming to the limit of my today's talk. We will continue tomorrow. Goodbye.
Goodbye.